This example shows you how you can do the hypothesis testing about the population mean when a standard deviation of the population is not known, and we are going to use Excel for this. A good example is the average price of a house or single-family residence SFR in Los Angeles County. We are doing a hypothesis test about the population mean, which means the average price of the population of single-family residence or houses in Los Angeles County when we don't know standard deviation or sigma of this population. So we don't know that. Okay, so the context is this. House prices have increased considerably in the past few years. In recent study, it was reported that SFR or single-family residence houses in Los Angeles County has a mean price of $1.5 million. This figure was an all-time high, or is an all-time high, and had increased nearly 50% over the previous 5 years. Assume that a current study is being conducted to determine if this average price is valid. So in this table, you can see the prices for a sample of 50 SFR houses sold recently in Los Angeles County. And you can see numbers, for example, first one, just $1.95 million, and so on and so forth. I mean, there are cheaper houses, for example, $750K roughly, and so on, so forth. So with this data, first question is, formulate the hypotheses that can be used to determine whether average SFR house price in Los Angeles County is $1.5 million. Okay, so what we are trying to say here is our null hypothesis, H sub 0, is the mu, or the mean of population, or basically the average house price in Los Angeles County is $1.5 million. The alternative test, H sub A, is then mu is not equal this price, is something else. For example, prices have changed so fast that the assumption or reported value of $1.5 million is not valid anymore. So it's a two-sided or two-tailed hypothesis testing. And because we don't know sigma, or the population standard deviation, and the sample size is just 50 houses, then we have to use t-distribution and t-statistic, a t-value basically. So we are talking about the distribution of, let's say, sample mean, which is the average price of SFR in the sample of 50 houses we have here, to be like this. And of course, it's an unbiased estimator, so we know that the mean, the expected value of the sample mean should fall on the actual population mean, whatever it is, mu. And we are using t-distribution, so this is the t-distribution PDF. So this is t-distribution. And t-value is on the x-axis. What we are trying to see is, with a confidence of 95%, or basically significance level, alpha equal to 0.05 is the significance level. So significance level, not going to write it, but basically with significance level of alpha equal to 0.05, what we are trying to say is we are trying to check if we have two vertical threshold lines here, in which if you add up the probability for the area of the highlighted, shaded lower tail and upper tail together equal to 0.05. So basically each of these areas corresponding to rejection region 0.025, and this area 0.025. These are the rejection regions for the null hypotheses. And also here is the rejection region for the null hypotheses. By rejection region, I mean if the t-value from, or test statistic t-value for this sample of 50 houses with the data shown here ends up to give you a t-value above this threshold line on the x-axis or below this threshold line on the x-axis here, then we're going to reject null hypotheses. So that's the plan. Okay, so we now have our null and alternative hypotheses. Let's deal with the test statistic. So as I said, for test statistic, we're going to use t-value, and we know t-value is just simply the sample mean, the average price of 50 houses provided in this sample, minus the hypothesized value of the population mean, which is $1.5 million. That's mu0, hypothesized value, and then divide by standard deviation of sample mean. And we know standard deviation of sample mean is just equal to standard deviation of provided sample divided by a square root of number of, or sample size basically, number of houses in the sample, which is 50. Okay, so we have we need to compute some of the information here, but we have n because we know n is 50. We need to compute sample standard deviation. This is, by the way, also referred to as a standard error. Standard error for sigma x bar. And this is sample standard deviation. Standard deviation. Okay, and x bar is sample mean. And mu0 is hypothesized value for population mean. Okay, so we just need to compute a couple of things. So what is x bar? That's the first thing. X bar is the sum of the values provided here. So x bar is equal to, okay, so let's add things up. So it would be, let's say the sum of, I would have preferred if these numbers would be in a column so that it's easier to deal with them, but it is what it is. Maybe we can just port them in a column. So we are dealing with this set of numbers, or actually, maybe I can just add them together. Good, okay. And then I would compute average. So we are talking about average. Great, okay, so we are talking about the average house price, or SFR, in Los Angeles County. The sample provided here is $1.6468 million. So that's the sample mean. Now, what is the standard deviation or sample standard deviation? So we have to compute that as well. So S is equal to, so I'm going to use the same formula. So this time it's equal to standard deviation, estimate a standard deviation based on a sample. Okay, so it's this value. Okay, so it's about $515,000 for the standard deviation of the sample we have here. So therefore, what we can compute from here is we can compute the standard error, which is sigma x bar, using this formula. So to do that, then I would say it's standard deviation of sample divided by, let me just also write down here, n equal to the sample size, equal to 50. So the standard error is equal to standard deviation divided by square root of sample size. Okay, so that's our sigma x bar. So then we can compute the t-value. So you would say test, maybe I can do it here. Maybe I can just write it here. So test statistic t-value is equal to, okay, so is equal to sample mean minus hypothesized value, $1.5 million. So that would be 1500, and then divide by the sigma x bar. Okay, so it's 1.93. That means we found the t-value for corresponding to test statistic that we have. We just need to check whether this t-value falls in any of these two upper or lower tail regions. If so, then we will reject. To do that, the best thing we can do at using a p-value approach is we already know what is the probability associated with either upper tail or lower tail, being 0.025 coming from alpha over 2 when alpha is given to us being 0.05 significance level. So I'm going to compute p-value. P-value is equal to, maybe I can shift it here. Okay, so p-value is equal to t. So what I'm computing now is t distribution values. So t distribution, let's say you're doing left side, it doesn't matter. Basically, I'm doing this value here. So t distribution here, yeah, it's good enough. Or maybe to the right-sided students t distribution. Let's do the t distribution, that's better. T distribution, the x value is the t-value provided here. So it's going to be 1.93. Degree of freedom is the sample size minus 1. That's the degree of freedom. And cumulative is true. You're doing CDF or cumulative distribution. Okay, so what is this number saying? This number says if the t-value is 1.93 and you're talking about somewhere on the x-axis here, then the area under the PDF or t distribution PDF on the left side would be 0.9703. So what I'm interested in is area on the right side. So what I need to do is just 1 minus this. So it's 0.03. Okay, so what I'm understanding now is this p-value that I obtained is greater than the alpha over 2 significance level recorded here. That's good news. I would say then, based on this information, I would say this is greater than alpha over 2. This is not actually your p-value, but comparison is with alpha over 2. If you want to compare with alpha, what you need to do to be accurate is you need to multiply this by 2. Because as I said, this is a two-sided or two-tailed distribution. What I computed here was the area, so if your t-value say here, let's say this is the line turn out to be, and this point is t equal to 1.93. Now, what we computed here before multiplying by a factor of 2 is the area under the curve on the right side. So this area basically. And that area before multiplying by 2 computed to be 0.03. Now, we also have, it's a two-sided, so we need to also consider t equal to negative 1.93 and the area under the curve on the left side of this vertical line. So that's why we need to multiply this by a factor of 2 for the two-sided or double-tailed hypothesis testing. So same idea. So p-value is 0.06 and it is greater than the significance level. So as a result of that, we would say, okay, using p-value approach, so using p-value approach or method, since p-value is greater than alpha, I mean, it's obvious, alpha is 0.05 given to you, significance level, And p-value you computed here is 0.06. Because of this, you would say, therefore, so you would say, since this is the case, we can't reject the null hypotheses. So basically what you're saying is you cannot say that the price is substantially different. The average price of SFR in Los Angeles County is substantially different than the hypothesized value of mu0 $1.5 million that is presented in this report. So that is our conclusion based on the significance level provided here, and that's the p-value we computed. Just on a side note, if you wanted to also compute the critical value, so critical value, then that means if you consider 0.025, then what is the t value corresponding to this threshold edge, which would result in the upper and lower area to be 0.025, basically alpha over 2. So that's the critical value. To compute critical value, we can also do that using Excel function, which is inverse t inverse. This function returns the left-tailed inverse of the student's t distribution. So I use that. I need to provide probability, which it is on the left side. So when I'm interested in 0.025, that's on the right side. I need to say 1 minus 0.025. So 1 minus alpha over 2, which is 0.025. And degree of freedom, which is n minus 1, 50 minus 1. There you go, roughly 2.01 critical value. So that means this point is approximately t value of 2.01, the critical value. So even using the critical value approach, you would end up, as expected, you would end up with the same outcome. So you would end up using, what we are saying is using critical value approach or method. You would say, since critical value is greater than test statistic p-value computed, therefore we can't reject null hypotheses H0, because critical value is 2.01, test statistic t-value computed is 1.93. This concludes this example. I hope that it illustrates how you can use Excel to run hypothesis testing for population mean when the standard deviation of population is not known and you have to rely on the standard deviation of the sample you have.